Okay, good afternoon. We can get started. Um, my name is Gaiman Yi. I'm the Technical Director of the I4 Energy Center. Welcome to today's seminar. I also want to welcome those that are viewing the seminar today on the internet. Today's speaker is Dr. Raju Pandey. He is an Associate Professor in the Computer Science Department at UC Davis. Dr. Pandey's current research involves building scalable, reliable, efficient, and secure system software infrastructure for sensor network-based systems. His research group is also developing fundamental techniques for building distributed systems that can dynamically adapt to changes in the environment and program characteristics. Dr. Pandey is also the co-founder and chief technology officer of SynapSense, a leading provider of energy efficiency-focused data center infrastructure management solutions. Dr. Pandey has a Bachelor of Technology from the Indian Institute of Technology, MS from the University of Massachusetts, and a PhD from the University of Texas. Let's welcome Dr. Pandey.
Thank you so much, Gaiman. Can you hear me? Okay, good. So, first of all, thank you so much for inviting me. I'm honored to be here. So what I'll do today is I'll talk about data center optimization. As Gaiman said, I wear two hats, one at UC Davis and another one at SynapSense. And the UC Davis hat works mostly on mobility and cloud and distributed system. And the SynapSense hat is on wireless sensor networks and data centers. So today I'll be wearing the SynapSense hat, and so all the credit for whatever I say today goes to the SynapSense engineering team and the services team. And so what I'll do today is I'll give you a framework that we are trying to develop at SynapSense. We are trying to understand how do you optimize data centers. I mean, if you look at the data center optimization problem, it's fairly simple. The problem is that you want to optimize resources that you want to give to your applications. And so it's quite straightforward. I mean, computer science has dealt with resource scheduling problems forever. So the question that we're going to look at today is, what is it that about data center that makes it so hard to optimize them? And in most cases, it's because of lack of information or because of lack of right information. So if you look at this first slide here, if you look at this thing here, you are, in most cases, the servers are idle almost 80%, 90% of the time. In many cases, the data center guys don't even know where their servers are. So what you're doing here is that you are providing 5 watts of energy for 1 watt of useful work. 80% of the time, this server is not doing anything. And if you extend it to the server hardware itself, then you're giving it about 18 watts for 1 watt of useful work. And if you extend it to the data center, you are basically giving it about 40 watts of information, 40 watts of energy to do 1 watt of useful work. And the primary reason is the disconnect that you have between the load that you have and the infrastructure that you have built to run that particular load. And that infrastructure involves the servers themselves and also the infrastructure that supports the server, which is the cooling or the power infrastructure. So the key problem here is that you have built these huge data centers, and you have provided all kinds of server resources and cooling resources and power resources. And now you're trying to optimize that resource without providing any connect between the load that you have and the resources that you have. So the key problem that we are trying to solve here is how do we provide the connect between the two? And so the vision for us for SynapSense is that how do we make these two talk to each other? How do we define a dynamic environment which allows us to understand where the load is? And then how do we adapt the underlying infrastructure to meet the requirements of these loads themselves? So this slide is fairly, it gives you our vision. This is where we want to be. This is not where we are today, but this is what we want to be. So what we have is we have a data center which provides you with all kinds of servers, okay? And then you have a model of the data center in terms of what kind of IT infrastructure do you have, what kind of hardware you have, what kind of software you have. And then you are going to now create a model of this data center in terms of what is the cooling and the power capacity you have. So you're continuously monitoring the data center. You're monitoring for the cooling infrastructure. You're monitoring for the power infrastructure. And from there, you're building what kind of cooling capacity you have, what kind of power capacity you have. And at the same time, you're also capturing what kind of information you have on the IT side. Okay? From this infrastructure, now you want to run a certain load. Now, in order to run this particular load, you want to figure out what kind of hardware you have, what kind of software you have, what kind of load you have running on these different servers. And based on all of these metrics that you collect, you're trying to figure out which is the right server for you that you want to run on. Okay? And once you have done that, then you're identifying the particular zones where these servers are going to run. You're going to identify the resources they're going to require. You're going to tell the system that, hey, go ahead and give me the right amount of cooling and the power that I'm going to need. Okay? And then you're going to build your virtual load or virtual application environment, and then you're going to dump it onto the data center, and it's going to run. So this is a fairly simplistic view that I'm going to give you, but the point that I'm trying to make here is that what you need is some kind of infrastructure management system, something which continuously understands the environment, which understands where your resources are, cooling, power, IT, whatever resources that you need. It understands what kind of load you need. It discovers those resources for you, the cooling and the power and the IT resources. And then it configures these resources for you. Okay? And then it provides these resources for you. So what we are looking for is to build the infrastructure which will allow you to adapt your underlying system to the needs that you have. Now, what we have done is that we are going in a slightly backward way. So what we have done is that we are starting from the cooling side and the power side. And what we are trying to do is that we are trying to build an infrastructure which will allow us to adapt that dynamic system. And once we can adapt that dynamic system, then we can start to adapt the IT side too. And there is a reason for it. The reason for it is that the IT side is the harder one. And it's not hard because it's a technical problem. It's hard because in order for you to dynamically adapt the IT load, you really need to understand the load and the load mix itself. And in most cases, if you go to most data centers, most data center operators do not have that knowledge. And that knowledge is going to develop over the next few years. So what we are trying to do at Synopsys is we are trying to build this infrastructure one by one, where we'll build and model and adapt the cooling and the power infrastructure. And then slowly we are going to build the IT infrastructure. As the IT knowledge builds up, we are going to combine these two to build one common, what we call as data center infrastructure management system. Okay? So what we look at is the framework that we have, we call 3Ms. And the infrastructure is that this system runs, and it's continuously monitoring your system. It's continuously monitoring for different kinds of modalities. And once it has understood what's going on in the data center, then it builds a model, analytical model of your data center. It understands where your resources are going. It characterizes your data center in terms of how good or bad your data center is with respect to these metrics. And then once it has built this model, it uses that model to basically adapt your system. And then this system is basically continuously going through this particular process itself. Okay? So let me just first go through the measure part. What are the things we are measuring today? So what we measure today, of course, is cooling and power. We also can measure servers' utility in terms of how loaded they are. We use all these different kinds of things like temperature, humidity, pressure, leak detection, anything physical that you want to measure, we can measure those either through a wireless network or a wired infrastructure. It doesn't matter how this resource comes from. And the way we do this measurement is that we deploy these devices on these different racks. Like for instance, these are the different temperature sensors at different places on the racks, which allow us to capture how the air is flowing and what kind of temperature you have each of these racks. We also deploy different kinds of pressure differential sensors in the floor itself. We deploy humidity sensors. We deploy sensors that allow us to capture how much liquid is going into the data center. We also have sensors which allow us to capture power at many different levels. So we can capture at the UPS level or the power circuits level, individual racks, or even individual servers themselves, we can do it. We have, from a communication network point of view, we have both data networks and control networks. For data networks, we use mesh, wireless mesh, for deploying many of these sensors. And this is just a very brief architecture of the network. It's a multi-gateway architecture, which allows us to collect information, scale the network to thousands of devices. It's adaptive in terms of channel hopping and all the usual good stuff that you see in wireless networks. We also support both IP networks as well as BACnet, Modbus, any of these networks that you use to collect information. But the key point here is that we really don't care how we are going to collect information. We are going to provide every possible protocol that you need to be able to access information. And in some cases, we use wireless. We use wireless because it's cheaper for us to deploy. We use wireless because we can extend it. We use wireless because we can make it very fine-grained. And one of the ways we use wireless also is to bridge to different kinds of devices. So we have these bridge devices which allow us to connect to the existing infrastructure and then understand what these devices are, understand the protocols, and then basically do the transformation from the protocols to the devices themselves. So we are starting to use the mesh wireless also for control. We are starting to slowly, very, very gingerly, we are starting to use it for control in some of the buildings. And of course, we use wired networks for connecting to any of the existing devices. Okay. One of the really interesting ways we use the wireless network here is the way we measure power at the server level. So we have this device which allows us to measure everything that you want to know about power at the server level. And what we have done is that in order to reduce the cost and reduce the information that you are collecting from these servers, we have basically built a multi-tiered network. And so at the top level of tier, you have the general purpose wireless sensor network. And the lower layer, you have these individual devices which are collecting power continuously, and they are sending it to a common bridge. And then the bridge is basically being used to integrate the information. Basically, we collect all the data that comes from the individual servers. We optimize the information. We reduce the information. We correlate information. So we can do a lot of processing about what a specific server is doing or what's going on within a server at that location itself. And then we use the wireless network to distribute the information back to the endpoints themselves. Okay? So as you can see that we have developed all kinds of devices, wireless devices, wired infrastructure to be able to collect very, very fine-grained information from very many different sources. And the key for us, I mean, one of the observations from me has been the fact that we go and deploy these devices ourselves, the fact that we know where you should put these devices, the fact that we know which information is useful allows us to go to the next level, which is how do you optimize, how do you model this information, how do you characterize the information that you're getting from these different sources. So the next part of the framework is the model part, where we build the semantic model of the data center. And by semantic model, we mean the asset model of the particular data center. That is, what is a data center? What kind of resources it has? And on top of that semantic model, we then build metrics. These metrics characterize how the air is flowing, how cool the infrastructure is, where the power is going, what are the efficiency of the entire system itself. And so, for instance, in one of the key metrics that we use for optimizing the data center is how the air is behaving in your data center itself. So for instance, if the air is going through the raised floor, if the air is coming this way and is going this way, is it going to the servers themselves, or is it bypassing all the way into the roof itself? Which means that if you have some kind of bypass air, you are losing some level of efficiency. So we use the sensor values to calculate what kind of bypass air or what kind of recirculation you have in the data centers. And these metrics, in a sense, start to characterize how good is your data center in terms of efficiency. That is the air going where it should be going? Okay, and So we have built different kinds of metrics. So things like rack cooling index, which allows us to measure how effective is your data center in terms of upper and lower bounds for each rack. So for instance, for every rack, you may set a certain bounds in terms of what the temperature should be at each of these particular racks. You can set individual bounds. You can set different sets of bounds. And so this allows us to calculate how good or bad is your system or is your data center in terms of keeping those bounds themselves. And so what we are doing here is that we are continuously calculating these bounds, and we are giving you a sense of what these bounds are in real time, so you know how changes in the data center, that is, once you make certain changes in the data center, how are these metrics getting affected. So return to RTI is a way of characterizing how much of the air, the cool air, is bypassing the entire system itself. And by calculating those continuously, you're able to see that when you make changes, how does it affect the pressure itself, or how does it affect the temperature distribution along a rack itself. We also have many other metrics, such as thermal anomaly matrix, which tells us that how the temperature is getting distributed across different planes in your data center. We have metrics for calculating the efficiency of the different kinds of equipment you have. And so what we are trying to do is that we are trying to characterize a resource in terms of how it's being used and where it's being used, and if this is being used in the most effective way. Okay? So here is an example of how rack cooling index was used. So what we did was we would go to a data center. So as part of Synapson's deployment, what we'll do is that we'll go to a data center, and we will go and deploy our sensors. The first thing we'll do is we'll deploy the sensors. We'll integrate with the existing infrastructure. And then once we have done the deployment and the integration, then we are going to optimize the data center. And the way we optimize the data center, and I'll talk about that in a few seconds, but just to summarize things here, we will basically use these metrics and the other tools that we have to look at how the changes that we make, how the changes the Synapson teams make impact the entire data center itself. So you can see that, if you look at this graph here, what is showing you is that how different changes are affecting the different RCI values. That is, are certain parts of the data center overcooled? Are certain parts of the data center are there hot spots in the data centers? And these metrics, in a very small summary, give you that, yes, there is some amount of hot spot in the data center. And then you can identify them by zooming into each of these metrics to the individual racks themselves. You can also look at how undercooled or how overcooled the system is by looking at these particular lines themselves. I mean, you don't need to look at individual data. Just by looking at a line, or you can put a certain bar saying anything below 95% is overcooled, or anything above 99% is okay. So you can set these bars, and then you can use these bars to very quickly understand whether your system is behaving in exactly the way that you had desired. I mean, it's a completely customizable system. So it depends on you where the bars that you set, and depending on those bars, we can characterize the behavior of the system in terms of these metrics. So for instance, if you see that vertical bar here, that vertical bar shows you that before the vertical bar was there, the system was behaving in a very nice way. We had every rack was within this parameter, and then something happened at that particular rack. Something happened after that point, and then things have changed. Okay? And then you can investigate what has changed by zooming into those different particular racks themselves. And we provide you with tools that allow you to basically direct yourself to not only a global view of the data center, but also the individual view of the system itself. Okay? This shows you, how you can, when you make certain changes in the data center, how these changes affect the recirculation air, for instance. Okay, so this shows you that as we made certain changes in the data center, the delta between the supply and the return temperature in different cross basically changed significantly, and that basically increased the efficiency of your cooling units themselves. So what I'm trying to say here is that these tools allow you to customize the behavior of your data center. These are basically knobs that you can use to play with your data center. And that's what we are looking for. We are looking for a set of high-level knobs, metrics that are based on analytical properties of your system. And then we want to be able to play with these knobs so that we can then optimize the behavior of the whole system itself. Okay? In addition to a lot of the cooling metrics, we also have developed a lot of power metrics, including PUE and DCIE. These are the standard metrics that are being used to characterize the power efficiency of the data center. And basically, they are very simple metric. They don't say much, but what they say is, in a sense, what they are saying is that how much of the power is going to do the useful work, in a sense. That's what they are trying to say. And there are two variations of it, PUE and DCIE. They are both connected, but basically they are saying that if I give 1 watt of power, how much of it is going to do something useful? And then we have developed other metrics as well, which try to characterize the power efficiency in terms of capacity and usage of capacity and things like that. Here is this chart basically shows you what is involved in building a PUE. And this is what we call is a PUE graph. And this is basically a data flow graph. And what this data flow graph does is that it understands every source of power and how they are all interconnected. So let me just show you a slide. So basically these are all the different sources that are connected through different computations, and then they form the entire PUE graph. So what you're doing is that you're trying to understand the source of power and how this power is flowing through your entire data center. And so you have this very complex graph, and at the end of that graph is what you have as the PUE, which is you are defining the metric of the entire data center in terms of overall power usage. But this graph allows you to go at any level, and you can assign any metric of power usage at any of these levels. So what you can do now is that once you have this graph, this how power flows through your entire data center, then you can start to use these metrics to see where your power is going and who is using how much power and what are the possible bottlenecks in this particular graph. So this can help you, again, optimize the power usage. It can help you understand where your losses are. It can help you understand which part of the data center is using how much resource. So it can help you understand which part of your IT load is using how much of the information. So this kind of tree allows us to start to connect how the resources are going to be used on the IT side to the usage of, or to the resource provisions themselves. And once we start to understand these two, then we can start to control the IT side as well. Okay? So this is the first step in understanding power usage on the overall power usage, basically. In addition to the metrics that we have also built lots of these imaging models, and these are really, really useful models. And I'll give you an example. This is an example of, it provides basically a overall view of the data center in terms of how the temperature distribution is. And there are 4 different views, so the top, middle, bottom, and the subfloor itself. And here is a real movie, actually, that I'm going to show you. This movie actually happened. If I can play it. I lost it. Let me try it again. Okay, anyway, let me not worry about the movie itself. Let me just say what goes on in the movie. I can see it, but okay, anyway, let's not waste time on it. So basically what the movie does is, this happened in a real data center, and what the movie shows you is that it's basically it's a continuous stream of these images. And as what happened in the data center was that there was a fault in one of the CRA units. And because of that, the amount of cooling that was going to the different racks went down quite significantly. And you can see, if I could play this movie, as to how these changes spread across the entire data center itself. I mean, it's amazing how I wish I could play this. See, even trying at home doesn't help. Oh, well, that's okay. I don't want to waste time on it. Okay, so that's the thermal images that give you the overall view of the data center in terms of how the temperature distribution is at multiple levels. Power imaging gives you a view in terms of where power is going. And it also gives you a view in terms of where power is available. So you can use this kind of tools to do capacity management, for instance. So you can use it for deciding where the servers should go. You can use it to decide where your load should go. You can use it to decide where your next set of racks are going to be. So these tools, the power capacity tools or what-if analysis tools, help you understand, one, where the resources are, two, understand who is using the resources, and third, they allow you to basically design the extensions to the data center in terms of resources themselves. So these tools allow you to basically play with the resources that you're going to need and play with how you're going to use them in future itself. Okay. This is basically a combination of both the cooling and the power combined together. And what this allows you to do, it allows you to understand where your IT infrastructure is using and what is the impact of that IT infrastructure on the cooling infrastructure itself. So you can use that to understand problems in your data center, for instance. Okay. Again, so these are visual tools that help a data center operator understand how the data center is behaving and to optimize it. In addition to these tools, as I said, we have these metrics which automatically help you understand where the problems are in the data center and help you point out to those places. Okay. So what we talked about was very quickly the different kinds of metrics we have, how we characterize the data center in terms of these metrics. Now I'm going to talk about the modification part. That is the part where we start to now adapt the data center in terms of the resource requirements. And so what we are doing here is, and this picture basically shows you is, and I'll go into a little bit more detail, is that once we have built the wireless sensor network or a sensor network, what it allows us to do is that it allows us to understand the relationship between the sources that are provided and the sources that are consumed. So these dependency relationship between the point where I have measured something and the point that provides that resource allows me to build these dependency networks in the data center itself. And now I can use that to adapt my system itself, and I'll show you how that is done. So we have built these different kinds of adaptation algorithms which allow us to modulate the temperature of the data center. It allows us to determine how much is the volume of air that's going to go into the data center, and we're starting to look at modulating the CPU throttling speeds and so on and so forth as well. Okay. So this shows you the different stages the control system takes a certain data center through, and I'll show some examples also. So the process of optimization for us is a three-step process. The first, of course, is the visibility. You really need to know where resources are. You really need to understand who the resources are, how the resources are being used. The second part of the process is the airflow management, and this is a manual process. This is the process where you are going to basically normalize your data center. This is the place where you're going to say, I'm going to make sure that my resources are going where they should be going. You're trying to remove any wrinkles that you have in your data center. And then once you have done the manual optimization, you have brought the data center into some normalcy, then you can start to adapt the system using automated mechanisms. And I'll talk about that in a second. Okay? So let me just go through the manual optimization process. And the process is fairly simple but very intensive. And intensive in the sense that what you have to do, I mean, the process, what you're trying to do is fairly simple. What you're trying to do is that you're trying to understand, based on the load you have, let's say the IT load, you're trying to understand how much air do I need, and what is the volume of the air that I'm going to need, and what should be the temperature of that particular air. That's it. That's all you're trying to do here. The part that becomes difficult is because when you go to these data centers, most of the data centers are in a fairly non-regular way. That is, the way they are organized, or the way the air flows, or the way you have anomalies in the data center because the data center hasn't been organized. it becomes a completely arduous task for you to, basically what you're doing is you are going through the data center one by one, row by row, rack by rack, trying to make sure that there are no airflow anomalies in the system. So as part of the process, what we do is that we will go and we will first understand how much volume of air you need. We'll calculate what is the temperature you need. Those things can be calculated pretty straightforward. After you have understood that, then what you do is that you go through each row and you start to look at what kind of load you have in each load. Now, this is the place where the lack of information starts to hurt you. If you knew how much load you have in each particular rack, if you could control the volume of the air that goes into each of the rows, it'll be much easier to do this task. But there is no such information. You don't have that information. So what you're trying to do is that you're trying to guess on the basis of the load that you see in the racks visually, and on the basis of how many tiles you have in each of these racks. And then you do a very simple calculation. You say, okay, I see 20 servers here, and I see five tiles here. I don't think I'm going to need so much volume of air here. And then you start to replace these tiles with the solid tiles. Basically what you're doing, you are manually controlling how much volume of air goes into each of these racks. Okay? And so what you are doing is that one by one, basically row by row, you go through the entire data center and you figure out how much volume each of them need. You replace all the tiles that you need. Then you look at all the places where you have all kinds of air mixing, things that are holes, things that are not tagged properly. And in a sense, if you think about it, you are basically cleaning up the data center. So you clean up the data center, and at the end of the data center, but what you get is incredible, actually, and I'll show you that. So this was one data center which we did, and it's a lot of hard work. I have done some, and man, it hurts. Okay, so what you have is that this is one of our smaller data centers. Imagine this is just 12,000 square foot. We have done 100, 200,000 square foot data centers, and we have done this to those. So you can imagine the amount of work that is involved. And the reason I'm explaining this to you is because I'm trying to show you that technical is not a great technical problem. It's a management problem in many cases. And in order for us to reach that ideal stage, we have to go through this particular stage. Okay? So this is a fairly small room. We have about 960 temperature sensors. The deployment of the sensors are shown here. So we have a tool which allows you to model the data center, and it allows you to understand where the different racks are, where the different cooling units are, how they're distributed, and based on the distribution and the deployment of your data center, we will basically build a deployment model for you, and deployment model will describe how the different sensors are located, where they're going to be located, how many sensors go in each of these things, and what kind of load balancing you need in terms of traffic, where the gateways are going to be, all those things, where the servers are going to be. So we'll build basically a deployment map for you, how we are going to integrate the entire infrastructure into your existing building management system or whatever you have. So we'll build this entire thing. And outcome of that is going to be this data center, which will basically capture, it captures the semantic model. It's a bottom-up model of your data center. Now, once I have that bottom of the model, I know what CROs you have. I know where they are located. I know what their capacity is. I know how much you can output. I know what your IT load is. Once I have instrumented it, now I can start to do something meaningful for them. I can start to optimize something. Okay, so what as I said, the first step was as we go through each of these racks, we are basically cleaning up your data center, and you can start to see. So this was the initial stage. This was the stage where the things were unbalanced. Okay, and the red means that you don't have enough pressure, and if you don't have enough pressure, which means you will have hot spots in those parts of the data center. You are pushing enough air, but it's not going to the right places. Basically this is what this is saying. Okay, green means I have okay amount of air. Red means I don't have enough air. Okay, and so what we did was, we started to go from one side, and systematically we started to plug all the holes, started to make sure that the air goes where it goes, started to take care of all the vents, and you can start to see that the pressure is starting to increase. Okay, that is, there is enough pressure It's just that it's not going in the right places. Okay? And so we went over, that was after 1 hour, 2 hours, it looks like this. Blue means good. There's a lot of pressure. And then after about 4 hours of hard work, it's all blue. What it says is that there is more than enough pressure. We are wasting energy, okay, by pumping so much air, but we are not pointing it at exactly the right places. Okay, so this was after we had cleaned it up after 4 years of floor balancing. Everything is running as it should be. Nothing has changed except the tiles have been removed and things have been cleaned up. This happened after what we did was we said, okay, since there is so much pressure in we don't need to run all of these crawlers at the highest possible speed. So we brought them down to a certain number, and those numbers can be calculated automatically. That's what the basis for our control algorithms is too. So based on what we know about your IT load, we can now start to reduce the fan speed, or we can start to increase the temperature of the air that goes into your data center so that we can achieve exactly the same thing as you had before, but now we can be much, much more efficient. Okay? So this was, we ramped down about 15 of these fans, and some data centers have hundreds of these fans. Okay? And when we calculated, the calculation was we were saving about 22 to 23% of the cooling energy just by doing this. That's it. Okay? And if you look at, and this was after ramping down 30 crop fans. So basically, we were able to reduce the fan speeds. This is manual, by the way. Somebody is sitting and turning down these knobs. Okay? And you can imagine trying to turn down 30 knobs. And you have to understand the order in which you have to turn these knobs. Okay? So you can understand the complexity of trying to manage a large data center which has large number of crawls manually. But this is what we have done so far is basically manually, systematically, one by one, based on the floor map we have. We are basically changing the nature of airflow in the data center. So this was after we had done the entire work. It saved about 22% on top of what they already had, and this is what you'll see that happened to the pressure as we went through the entire process itself. That is, this is how it was. Okay, at 50% of the speed, we started the optimization here. Look how the air pressure went in for all of them. And then we reduced the fan speed to come almost to exactly the same safe level. That is, everyone is getting the same amount of pressure that they should be. Everyone is getting the right amount of volume of air that they should be getting. And now we can start to work with the temperature, start to work with temperature and bring the temperature down to the right level itself. So that's the process we do for manual optimization. But you can see that it's not going to work. This is good for a few days. And once you start to bring in new load, once you start to move your racks, once somebody starts to make all those mistakes, you're back to the same. You won't be back to the same again. We do have deployments where we have only done manual optimization, and they are still okay, but you are not going to be able to guarantee that it's going to remain in that stage continuously over time. You need an automated way to do it. Okay, you need a way which allows you to understand how your system is changing, and it allows you to adapt to those particular changes themselves. Okay, so we built after we did this part. After we understood the manual optimization process, we said, we have to build a control system to do it. And the control system is fairly simple, actually, if you think about it. The control system is, we are going to measure continuously. We are going to constantly measure it. We are going to pick a few metrics, and we are going to use those metrics to decide whether we need to turn the knobs up or turn the knobs down. That's all. That's all we are going to do in a sense. But the process is fairly complicated, and the process is complicated because of the distributed nature of the system itself. So we built. People are really scared of control system. They really don't want you to touch it. You need to really. They need to trust you. They really need to trust you to allow you to control their system itself. So it took us some time for us to show it to them. And one of the ways we have tried to build this control system is by showing them that our control system is completely reliable. I mean, we have built all kinds of fail-safe methods. We have built, we have brought the best of computer science into building this control system. That is, how do you build a fault-tolerant system? We know how to build them. And we have built it secure. We have brought all the best of the security that we have learned from computer science. We have brought all of that. So the system is fairly reliable. We have proven it to many of the people who commission these systems. We have proven that even if there are failures in the system, our system is going to continue to operate safely. Nothing will go wrong. That is, we have guaranteed that. And at the same time, we also are guaranteeing that the system is going to do good stuff. That is, it's going to reduce energy usage in terms of, how without the control system and with respect to the control system. Our system will continue to help you with energy uses. And one of the things, I mean, from a technical point of view, it's a great piece of software. There's no doubt about that. But, from a business point of view, and I'm giving a business point of view, people don't care. People care only about the fact that does it save me energy? Okay, and that's what we sell. That's what Synapsense sells. Synapsense sells our control system as a way to save money. That's it. What we don't talk about are all these great features that you have in the. I mean, one of the things it does, and we have not been able to sell them in terms of the level of reliability that it provides. If any CRAW or any cooling unit dies in your data center, this will scale. It will find the right resources for you, and I'll show you how it does that. It will scale, it will find the right resources. It will make sure that resource that it finds is the right resource. It will put it at the right level itself because it knows all the data that it needs to be. It has all the sensor information that it needs to. But we have never sold that part, the reliability and the scale part. That is, you bring a new cooling unit and you bring 20 more servers and you put it in these data centers and the system will scale. You don't need to do anything. It's like the way we have in computing. You add more resources and the system scales to use those resources. And we can do that here. You add more sensors, and that's where wireless becomes very, very useful. That is, you add 5 racks, you put down 3 sensors, that's it. You don't need to do anything, no configuration, nothing, no needed. It becomes part of the networks, it becomes part of the model, starts to build a model for your data centers, and then you start to use it to adapt the system itself. So let me just give you, I have 5 minutes. So let me just give you what we do for the control system and why it's a pretty interesting problem too. The problem was that you have, these are the 4 cooling units, CU1 through CU4. And what you're trying to do is that you are trying to understand how each of these guys affect certain portions of the data center itself. And so what we are trying to do is that we have these sensors. So what we do is that as part of the configuration process, we try to understand the relationship between the CRAW units and the different points. So we try to understand 2 things. One, we try to understand A affects B, and I can do that by changing how a certain CRAW changes and how it affects the behavior of that particular point or a sensing point. And that's why you need to normalize the data center. That's why you need to manually optimize it. That's why it makes sense to do that before you go and do the control. So the first point, that is A affects B, I need to know. And the second thing I need to know is how much do I change A that will affect the change in B itself. And if I can model those 2, then I can start to really have a very sophisticated control system. And so the way we do it is that you have the wireless sensors, temperature and pressure sensors. And then what you do is that you are basically calibrating by understanding what we call as region of influences. You're trying to understand how different points in the data center are affected by changes in the different cooling units. And once we understand these regions of influences, then what we do is that as you make changes, if there are changes in any parts of the data center, each of the device precisely knows which are the cooling units that need to be affected. And so I can now send those messages all the way to a centralized control unit. The centralized control unit is constantly processing information about how your data center is changing. And our sensors are fairly sophisticated in terms of they are not just sensing what the temperature is, but they are sensing the deltas and second order deltas. And they're also using the past behavior to predict certain future behavior as to how they think it might change. So we are always proactively letting the control unit know how the system might be changing. And based on those things, the control system basically then goes and connects to the right control units and then basically uses different control algorithms to turn fans on, off, temperature on, off, and down. So, so right now this is a completely centralized system. I mean, there is one single brain, I mean multiple brains, so these are all replicated, but there is one single brain which is basically doing the entire control system, which is not a great solution actually. So our next one is going to be a distributed one where, I mean, imagine, I really don't need to come all the way here. If I know that I'm changing and this is the one who's affecting it, I should be able to go and talk to these guys directly. And that's where we are going. I mean, we are building a control system which is going to be a distributed one. And that's what I meant when I said we are slowly starting to, take baby steps to make it wireless based. I mean, we don't know fully yet, but that's where we are going. We are going to build these distributed control systems where it makes sense too that if you have a small change local, why do you want to make it a global control system? Why not make it a local control system? So we are going in that area. This is our architecture. I don't think this is interesting. I'll just skip. I think I'm almost run out of time. So let me just summarize it. As I said before, I mean, what we are trying to do, as I said, we started early with the vision is we are going to understand how your data center is changing. I mean, that's the key. You have to be able to understand how your data center is changing. And once you are able to understand how it's changing in some form, using some metrics, using some sensors, some kind of measurement that allows you to predict how this system is behaving, and once we understand that, we can start to predict how to make changes so that I can optimize the usage of resources. Today, Synopsys is mostly doing on the cooling side. We are starting to look at IT side, and it makes sense because cooling is the second order effect. We want to be able to understand how the IT loads are changing, how the IT requirements are, and then use that to then decide where that load should go, and then use that to decide what the cooling or the power infrastructure should go. So that's where we are going. Today we are doing all kinds of control system for every possible scenario you can imagine, cracks and overhead. We are doing all of that. But ultimately where we want to be is the place where we have a very dynamic system, a system which is continuously monitoring, continuously analyzing, characterizing, building models, and then adapting your system continuously. Okay?
Thank you. Let's open the floor up for questions.
Thank you. I'm very interested to hear you describe that most of the data centers are overcooled. We work in the office buildings, and in US, office buildings severely, summer is cooler than winters. That costs a lot of energy. So we are looking at the reasons why this happened. And do you have some reasons why the data center is also overcooled? Is the system too big, or the standard, or the operation they thinks the cooler better, or do you have any
I think it's
explanation?
Some of it is, so the question is, why do you think data centers are overcooled? I think a lot of it is cultural, in the sense that people who manage data centers, they are awarded for making sure that their devices run 100% of the time. They are not rewarded for how much resources they are using. So the cooler the data center is, at least in their mind, safer their equipment is. So I think a lot of it is cultural. In fact, there are many places, many data center deployments that we have gone to, and people will refuse to increase the temperature because they are scared that the system is not going to work. I don't know what was your experience, but our experience has been, a lot of it is cultural.
The opening that you set up on where the waste goes. Mm-hmm. So that broadening that cultural one, I was struck that if we draw the analog with transportation, mm-hmm. So there we're very comfortable with the notion of well to wheels.
Yeah.
And we understand the loss at each of the stages. And of course, ultimately, it's about miles per gallon. And that somehow that gets lost in this world. And if, if these folks looked at their data center and it looked like, a whole fleet sitting there with its wheels spinning in the driveway doing nothing, it would be hard to accept that as reasonable just because they're sure the car would start in the morning.
Yeah, that's exactly. And in fact, I wouldn't, it's almost like a superstition. It's almost a superstition that if I turn this down, it's not going to come up. And I think sometimes, as a computer scientist, I feel we did a bad job of building these systems and operating systems. It's terrible, actually. Yeah. Mm-hmm.
You said that you have worked on data centers in a wide variety of sizes. And in a previous lecture, we heard that data center efficiency is generally optimal at the largest sizes of data centers. And this raises questions of market competition and regulation and monopoly pricing and so forth. So I'm wondering if your experience allows you to say which sizes are the ones at which data centers can operate most efficiently.
As I said, we have seen every possible size, and we have seen efficiency in almost all of them. And I would say if you look at what data centers do, basically what they do is that they are running these machines, and somebody is providing cooling and power. So the larger the system, the more efficient you are. No doubt about that. Because the smaller amount you have to buy all kinds of supporting infrastructure for the smaller one. So it makes sense to make it bigger and bigger. And that's why you see all these colos and all these companies building large data centers. And in few years, 5 years, all these small data centers are going to go away. It doesn't make sense to build your own data center, to have expertise to run these data centers, and then to care for the risks and the rest. And so, it's all going towards large data centers. As far as inefficiency is concerned, the problem you have in large data centers is because of lack of tools. So what you don't have is some way for you to be able to account for your resources that you have today. I always think of this as a closet cleaning problem. We all have messy closets, and the reason we have messy closets is because we really don't know what we have inside those. And that's the problem with a lot of these data centers. So you don't have nice tools that allow you to know what servers I have. I've read statistics where it says people don't know 10% of their servers where they are, and that's imagine for a large data center. They don't know what kind of cooling unit they have. They don't know how old they are. They don't know how they are progressing. They don't know what their performance is. So it's a lack of tools that makes it hard for you to manage these large data centers. And that's why over time, they start to operate worse and worse and worse. And over the next few years, I'm convinced that over the next few years, that's going to change. You're going to have all kinds of these dynamic tools, and there's this huge industry of what is called data center infrastructure management that's coming up. And they are trying to do exactly that. They are trying to build an accounting system which tells you where your resources are, how much you're using, and you're not using in the right way.
How about building a taller structure, ceiling? Is that effective?
The taller ceiling structures basically allow you to, I have seen some data centers which have very tall ceilings, and it's just a question of, your hot air goes up. So yes, you are, when we looked at, if you look at this slide, find it. So if you look at this one here, if this is taller, which means that you are going to reduce the amount of recirculation that you are going to have in the building itself. But at the same time now, you may be cooling the larger portion of the building. So there is a trade-off between how high your system could be and efficiency of cooling larger building plus reducing the recirculation air itself.
I have a question.
Okay.
So as more systems like yours are implemented and there's more lessons learned, has it had an effect on how future data centers are designed?
It actually, future data centers are already getting designed to very, very efficient. I mean, I'm sure you have seen data centers from Yahoo and all these guys, Facebook and Google. They have PUE in terms of 1.05, 1.1, very, very efficient data centers. So yeah, people are starting to understand how. I mean, it's all they are starting to understand the cooling side of it. That is, how do you manage the cooling side? But the IT side is still not done. I mean, there is a lot of interest in cloud computing, public and private clouds that you're seeing, and virtualization. But the easy part is getting done right now, which is you are virtualizing the hardware resources, which is easy to do. The hard part is to understand the mix of the load and be able to schedule that. And that knowledge is still not there fully formalized in some form, so that you can come up with a set of policy language which says, I have load A, which should run on July 24th at 5 o'clock because I'm paying so much power for power. That is not there yet, and it will come. It will come over the next few years.
Yep, great. Thank you. I think that's it. No more questions. Thank you very much.
Thank you so much.